Aliens, every science channel's favourite topic of discussion. Let's face it, it's a standard move in the clickbait playbook to suggest aliens are out there or interpret ambiguous signals as evidence for aliens. I'm sure you've seen stuff like this. The most ridiculous examples typically feature Michio Kaku's face and some outrageous headline. So clearly I'm making a huge YouTube mistake by making a video which goes the other way, but for the last few years I've become increasingly concerned about the problem that I'll discuss with you today. This is an idea which myself and Grant Lewis, who you might have seen in Veritasium's videos, have finally put together into a new submitted research paper, which I'll link to down below in the description. And by the way, this research was supported by many of you, our viewers, supporters to the Cool Worlds Lab research program, which starts from as little as the cost of a coffee once per month. Okay, let's start with the thought experiment, one first posed in 1968 by legendary physicist and statistician Edwin Jaynes. Imagine that you approach a table covered by many flasks of water. The volume of water in each is about the same, but of course small variations exist. Likewise, the room is pretty much the same temperature and pressure at all locations, but slight variations naturally exist here too. Next, I hand you a random chemical, let's call it compound X, and I ask you the following question. In what percentage of these flasks of water will compound X dissolve? Give me your best guess. Now, if you have no prior information, Jaynes argued that one might reasonably guess either 0%, or 100%, or numbers very close to that, like 1% and 99%, to account for the slight differences between the water. However, Jaynes argued that it would be very unintuitive to guess a number of around 50%, because if it was 50%, then it would imply that the small differences from flask to flask were sufficient to tip the solubility either way. In other words, if this was true, then the conditions in the room would have to be almost perfectly set to the threshold point between dissolving and not dissolving, balanced on a knife edge. Unless someone is playing a cruel trick on you, such fine-tuning would be surprising, and thus Jaynes concluded that the probability chart should look something like this. A high probability of 0% and equally so for 100%, but crucially, a valley of improbability between them. This thought experiment provides some conceptual understanding, but Jaynes went far further than this and rigorously proved that this must be true, and he is now credited as one of the founders of what we now call objective Bayesianism in modern statistics. Now, Jaynes never really thought about applying this to astrobiology, but for me, ever since I heard about this thought experiment, the connection was obvious. But instead of those flasks of water, we would now have possible seats for life, like star systems. And instead of asking whether compound X dissolves or not, we instead ask whether intelligent life eventually develops or not. When we look out at the stars in the sky, we wonder what percentage of them could have intelligent life. Jaynes already seems to provide us the answer. It is likely a number either hovering around 0% or nearly 100%. To quote Arthur C. Clarke, both are equally terrifying. Now, a basic question that one might have at this point is, how does this all square with the famous Drake equation, which defines the number of communicative intelligences in the galaxy, n, as a product of 7 input variables? I know, before you comment, many of you hate the Drake equation. Trust me, I hear you. But I think it's become popular to dunk on the Drake equation without actually paying attention to what Drake said. The real reason why the Drake equation's reputation has been dragged through the dirt is because it is an equation which has been misused and frankly even abused. You're not supposed to guess random values, plug them in, and then write a new paper proclaiming that there are 42 civilizations in the galaxy. It's too long of a topic to get into today, but fortunately I have made a double-parter video all about this up here. So if we can accept for the moment that in principle a Drake-like equation should be possible, then it seems in tension with Jaynes' perspective, who argued for a kind of all-or-nothing type scenario. A ninja move in our new paper is that we prove that the two perspectives can be unified by adding in a new element into the Drake equation, which frankly should have been added in long ago for it to make any sense. As it stands, the Drake equation is essentially unbounded. Yes, we have some constraints on a few of the terms, but that's not really what I mean. What I mean is that even prior to having any constraints on these terms, one can make the Drake equation predict arbitrarily large numbers of civilizations out there. As an example, let's set all the fraction terms to 1, civilization lifetime to 10 billion years, and the star formation rate to say 100 stars per year. Congratulations, you now have 1 trillion stars in the Milky Way that have civilizations around them. The problem is that there aren't 1 trillion stars in the galaxy to begin with. This is why the canonical framing of the Drake equation makes no sense. There are many of the problems with the Drake equation too, like here we have 7 input variables, but why should it be 7? We could easily extend that to far larger numbers. Someone might reasonably say that we should add a fraction for how often multicellular life develops as a critical step. And someone else might argue that we need language development as another critical step, and so on and so on. For years, I've argued that we should just do away with this specific formulation and instead strip it down to the simplest form we can, what I call the birth-death formalism. In any volume, be it a galaxy or a supercluster, the number of civilizations present must be a balance of birth and death. Some number of civilizations are emerging each year and some are dying. Drake's original equation is an overly elaborate version of this idea, with the first 6 terms in fact representing the birth rate and the last term being the reciprocal death rate. In my opinion, it is all of these extra details that cause the problems and criticisms often levied at the Drake equation. Far better just to boil it down to the process of birth and death. After some settling time, we should expect the galactic population to reach an equilibrium point, for which the number of births per year equals the number of deaths per year. Balance.
Perfectly balanced, as all things should be.
The total number of births per unit time must simply be the birth rate per location multiplied by the number of unoccupied stars, which is the number of total stars minus those already occupied. Similarly, the number of deaths per unit time is the average death rate per location multiplied by the number of occupied stars. Equating these two is the balance point, a steady state condition. Rearranging this a little, we can write that the fraction of stars which are occupied must equal this. In fact, for notational convenience, let's call this F, the occupation fraction, and this term on the right, lambda BD, the birth to death rate ratio. Now, so far, all we have assumed is that the galactic population is in a steady state. That is to say, it is not going through a dramatic episode of population explosion or decline. Also, I've been referring to stars a lot here, but you can switch that out for planets or even cubic light years if you prefer. The equation still holds. Finally, we are being agnostic about the mechanism of birth and deaths here. Births could be spontaneous or they could be through empire building. Likewise, deaths could be due to internal forces or external ones. In any case, the equation still holds. So let's make our graph of this F term, the fraction of stars which are occupied by an intelligent civilization. Starting over here, when the birth-to-death rate ratio is tiny, there are hardly any births, and anyone who does get born dies pretty quickly. As a result, the galaxy is nearly empty. As we dial this ratio up though, we get more and more civilizations. Eventually, increasing the birth-to-death rate ratio any higher has diminishing returns. By this point, nearly the entire galaxy is already occupied. There's just not much benefit in pumping it up any further. If the shape of this curve looks familiar to you, it should. This S-shaped curve appears in the real world all the time, including in ecological systems, a fact known since at least the 19th century. For example, if you let mold grow on a piece of bread, we start out with very little mold and then we see it spread rapidly before finally getting to a state where growth stalls because there's basically no bread left anymore. Like civilizations in a galaxy, we can't have more mold than there is substrate. Another example is tech adoption. So you have your early adopters buying that first generation iPhone, and then the mainstream gets in on it before eventually growth stalls because now everyone has an iPhone and Apple have approached a ceiling in sales. The birth-death formalism solves the issue of Drake's original equation being unbounded, as well as littered with arbitrary and poorly defined terms. Great, but how does this connect back to Jaynes, to his all-or-nothing conclusion? Well, it's apparent from looking again at this curve. Previously, I set the minimum and maximum x-axis values to be 10 to the minus 3 and 10 to the positive 3. But truthfully, the numbers could be much, much more extreme than this. Let's extend the axes out to account for our ignorance here. In doing so, the neck of the S-curve gets narrower and narrower. In this picture, there is a huge range of parameter space where the galaxy is nearly empty, and there is a huge range of parameter space where the galaxy is nearly full. But only a tiny, tiny slither of parameter space where we have intermediate values. In other words, this is finely tuned. This is the connection we've been looking for back to Jaynes. In fact, in our paper, we formally prove this. If we adopt a log uniform prior for lambda BD, which is the typical uninformative prior for a scale parameter like this, then we in fact prove that f follows Jaynes' original distribution. We get all the way back to his result.
See that?
So there's something profound here. Not only have we connected the viewpoints of Drake and Jaynes together, but we have revealed that the conclusion is the same for both. The galaxy is either teeming with intelligent civilizations, or it's nearly devoid of them. But something in between is highly contrived. This conclusion poses a challenge for those seeking the signatures of technological civilizations out there, because, let's face it, it seems pretty unrealistic that nearly every single star has a technological civilization around it. After decades of listening for radio signatures, we only hear silence. We don't see engineered stars littered across space or laser beams sweeping the sky. Indeed, we don't see anything out there that cannot be explained by natural law. If the occupation fraction really was close to 100%, then I think we'd really have to do some mental gymnastics here to make sense of how astronomers just seem to see a lonely empty galaxy. Yet more, even Earth's history proves this is contrived, since technology has only been around for a tiny fraction of its entire lifetime. So, if we dismiss the high occupation scenario, then there's really only two options left. One is that the answer is somewhere on the neck of that S-curve, or equivalently in Jaynes' valley of improbability. Or two, the answer is somewhere in the quasi-plateau of a desolate galaxy, which objectively is a far more likely outcome. Hence the title of this video and also our paper, where really what we're saying is that anyone hoping to detect an alien signal is implicitly betting that the improbable valley is somehow probable against all of the odds. When I came to this conclusion, I felt torn, even a little distressed, because for me, the search for extraterrestrial intelligence is one of the most exciting and special endeavors out there. I grew up dreaming of searching for alien life. So let's just be clear, I have zero desire or intent to tell you that it is a waste of resources. But at the same time, that naively seems to be what our results imply. So I have, of course, been desperately trying to rip apart my own paper and try to find some way out of this, which, by the way, is actually good practice anytime you write a scientific paper. There's a couple of escape routes we could try here, two cards we might pull to try and wriggle our way out of this box. The first is that we may indeed be on this plateau of a mostly lonely galaxy, but that's okay, because the plateau doesn't say that nobody is out there, it just says that very few are. So, to overcome it, all we need to do is dial up our survey size. Modern SETI surveys typically cover about 10,000 stars or so, but of course there's another 100 billion to go just in our own galaxy. Perhaps then we just need to up the ante and we will hit success. Mathematically, success requires that lambda BD is some number greater than the reciprocal of the number of stars in our sample, but at the same time it must be less than roughly 1, else we'd approach the filled galaxy scenario that we've already discounted. The problem is that even if our sample was the entire galaxy, some 10 to the 11 stars, there's no obvious lower limit on just how ridiculously small lambda BD could be. There's no useful theory of civilization birth and death rates. As an example, let's say the true value was 10 to the power minus 30. In that case, even after surveying the entire galaxy, the probability of finding another civilization would be 10 to the power minus 19, an unthinkably fringe outcome. And here's the kicker. There is absolutely no reason why lambda BD could not indeed be 10 to the power minus 30, or indeed a value far, far smaller. Now, yes, one can have a personal preference for a higher value, but critically, one cannot justify that from an evidential position.
What is faith? It is belief in the absence of evidence. Now, I don't propose to tell anybody what to believe, but for me, believing when there's no compelling evidence is a mistake. The idea is to withhold belief until there is compelling evidence.
Perhaps a more promising avenue is to violate the fundamental assumption of our work, that the population of the galaxy exists in a steady state of birth-death balance. Remember, that's basically the only assumption we make. Now, if this were true, then either the population would be in a state of decline, or alternatively, an ascent. A decline seems immediately improbable. There is nothing about the universe which is making it less hospitable over time. In fact, really quite the opposite. If anything, the early universe was a far more hostile place, littered with gamma-ray bursts, supernovae, and rapid star formation phases. A population in ascent seems more plausible. Perhaps a galactic empire is in ascendance and thus engineering lambda B upwards over time through some colonization programs. This is perfectly possible, and I know there are many persuasive proponents of this idea, but for me, this actually introduces another fine-tuning problem. To see this, consider that even traveling at the speed of our existing space probes, it should be possible to colonize the entire galaxy in a much briefer time span than the galaxy's current age. When sped up over cosmic timescales, colonization waves look like almost immediate phase transitions. They happen very quickly. So, three options exist. Either we live before this colonizing civilization ever emerged, in which case there's no one to talk to, or we live during the expansion phase, which is an incredibly brief episode in cosmic history, remember, or we live post-colonization phase, which contradicts our observations of the galaxy. So, despite my best efforts, I personally can't find a way out of the pessimism our paper implies. Despite all of this, there are two reasons why we should keep searching for alien life. First, the potential return. Yes, the probability might be small, but the ROI could be incalculable. The greatest discovery in all of science. If we give up and we stop searching, then we guarantee not detecting anything. And second, perhaps we really are in the filled galaxy scenario after all, something I discarded as incompatible with observations earlier. So how can that be? Well, so far I've been talking exclusively about technological civilizations, which indeed seem to be ostensibly rare, but I certainly cannot discard the idea of simple life being around nearly every star in the universe. The truth is that we have no observational constraints of that at all, and ubiquitous life is consistent with Earth's history and geography. And who knows, maybe they do go on to develop technology very often too. It's just that it looks nothing like anything we can even really imagine. So when we look out and see an apparently empty galaxy, perhaps it's just because we can't see the forest for the trees. We're not looking in the right way. If so, we need to diversify our methods, not just aim to increase our sample size ad infinitum. My thinking on this topic has been evolving over the last few years, as you have seen right here in real time on this channel, and I'm sure it will continue to do so in the future as well. But you know what? That is how science works. We iterate, we don't stagnate. I think that Jaynes' perspective is a very valuable way to approach this problem. We sometimes forget the wisdom from the past. Hopefully, this starts new discussions on how to proceed going forward. For me, this is always such a fascinating topic to wrestle with that I'm sure I'll be pondering these questions until my final days. As creatures of curiosity, we can't help it. Like an insatiable itch that we're drawn back to over and over again in the hope that one day we might finally crack it. So, until next time, stay thoughtful and stay curious. Thanks so much for watching. If you enjoyed this, then please do consider hitting the like and subscribe buttons. Those two little actions really do help us out. And if you haven't already, you might want to check out the Cool Worlds podcast for many more great conversations. Look, if you're trying to find a way to support everything we're doing here, from the research to the podcast to the YouTube channel, then the best way to do so is to use the link up above and down below, where you can become a supporter to my research team, the Cool Worlds Lab, from as little as the price of a coffee per month, with access to all kinds of special perks. So please do check it out. And thanks again for watching.